And the very good thing illustrated in the middle there, if you would scratch the surface, this passive film has a self-healing effect. So it directly will start to be rebuilt, as illustrated to the right there. And this is a very thin layer. If you consider a steel sheet, only 1 millimeter, and consider how thin this layer is on the top, we can compare this 1 millimeter stainless steel sheet with a 10-story building. Then the thickness of the passive layer is similar as a playing card on top of a 10-story building. Then you can understand how thin it is, but still so important and gives the corrosion resistance of the stainless steels. You need at least 10.5% chromium. There are a lot of different types of stainless steel, and they are characterized by their structure or microstructure. The most common one is the austenitic stainless steel. Then we have the ferritic stainless steel. And thirdly, we have the duplex, which is a dual structure of about 50% ferrite and 50% austenite. And then finally, we have the martensitic stainless steel. And then there could be other version connecting those together, but these are the 4 main ones. So if we're looking at what makes the difference here, we have up in the left corner, we have the austenitic stainless steel, and there the atoms are like arranged in what we call a face-centered cubic structure, whereas the ferritic stainless steel have a body-centered cubic structure. We will come back to that to understand what is the difference there. And as you can see illustrated here with the microstructure in a microscope, the austenite here is lighter and the ferrite is darker. And that you can see there on the duplex stainless steel micrographs that you have a substrate of the darker ferrite, and you have like elongated islands on top the lighter, that is the austenite. And you see you have about 50% of each structure there. And coming back to the difference between the austenite and the ferrite, of course, depends on specifically the alloying element, if they promote an austenitic structure or a ferritic structure. We'll come back to that. But what you see here is how the atoms are arranged in the microstructure. So in the face-centered cubic structure, each atom has 12 neighboring atoms there. Whereas in the ferritic structure, where you have a body-centered cubic structure, you see that each atom have 8 neighbors. So it looks a bit different. And the FCC structure is more closely packed than the ferritic BCC structure. Then finally, the martensitic structure. That is basically, if you're looking at alloying composition, like a ferritic stainless steel, but you have much more carbon in the structure. So by fast cooling, quenching, you will trap all the carbon in the structure. And from the BCC structure, it will be more deformed to be called the body-centered tetragonal structure, BCT structure. So you trap a lot of carbon in there, and it will be a very hard material due to that fact. So if we're looking at the influence of different alloying element, of course, it's a steel, so the most of it is actually iron, but then we add alloying element, and some of the alloying element is ferrite stabilizers, meaning that they will promote a ferritic structure. And as we already know, the most important alloying element is chromium. The chromium gives the basic corrosion resistance. It's needed there to create the passive layer. So the corrosion resistance increases with increasing chromium content. The chromium is also important to resistant to oxidation, so at use at very high temperature. That was chromium. Then we continue with molybdenum. Molybdenum increases resistance to general and localized corrosion even further, and we will come back to that, at least today, related to localized corrosion to see the beneficial effect of molybdenum. Then we have silicon. It increases the resistance to oxidation at high temperature as well. So the combination of chromium, silicon is important for the high temperature resistance. Then finally on this slide, we have titanium. In austenitic steel, they sometimes added to increase the resistance to intergranular corrosion, and also increases the mechanical properties at high temperature. In ferritic stainless steel, titanium is added to improve toughness and also to improve the weldability, to control the grain growth during welding and to avoid transforming the structure into martensite during welding. And it also increases the resistance to intergranular corrosion, which is similar to what it will do in an austenitic stainless steel. So now we come to those that promoting the austenitic structure, and there the most important alloy element is nickel. Nickel also increases the ductility and toughness of the stainless steel. It also reduces the corrosion rate in acidic environment. But looking at the localized corrosion resistance, as we will see soon, nickel doesn't have a big influence. So it's typically when you have an acidic environment, you can see the benefits. So the most important aspect of nickel is to actually be able to create the austenitic structure, which has a very high ductility and toughness. Then we have nitrogen. You're adding just small amount of nitrogen, but it has a beneficial effect both on the mechanical strength, but also on the resistance to localized corrosion, particularly if you combine it with molybdenum, and that is what we will see soon here. Carbon increases the hardness and strength of the martensitic stainless steel, as I mentioned earlier. It also reduces the resistance to intergranular corrosion. So you want to keep the carbon content low in most cases, except for the martensitic grade. And it strongly reduces both toughness and corrosion resistance in ferritic stainless steel, and actually also for martensitic stainless steel. Then the manganese finally increases the solubility of nitrogen and is used to obtain higher nitrogen content of austenitic or ferritic austenitic steel. And sometimes what we'll see in the lean duplex steel, nickel, which is an expensive alloying element, is replaced by manganese. Then we continue with the austenite stabilizers. Sometimes we are adding small amount of copper, which enhances the corrosion resistance in reducing acids, like sulfuric acid. Other important element for austenitic grades is that you can add sulfur. That will increase the machinability. However, it reduces corrosion resistance, ductility, and weldability. So you have to be careful which sulfur content you have there, which property you want to promote there. Then cerium finally is a rare earth metal, and it's added in very small amount in some heat resistant grade to improve both the oxidation and the high temperature corrosion properties. So sometimes we use what is called a Scheffler diagram to see how those austenite stabilizers versus the ferrite stabilizers will actually affect which type of structure you will get. Most importantly, you're using this type of diagrams for welding to make sure you will have the right phase balance in the weld metal compared to the base metal. But there you can see if you have, if the austenite stabilizer, the nickel equivalent, as you see there at the top of the graph, if that is high, then you will most likely have an austenitic structure. If you have a high chrome equivalent, a high level on the ferrite stabilizer, you see you would either have a ferritic, or if you're a bit higher on the austenitic side, you will have a duplex structure. And then for the martensitic grade, you mainly have the chrome, but also some austenitic stabilizers there. But most importantly, there you have a higher carbon content. Material selection, we will not talk so much about that today, but of course, depending on which properties you want to promote, of course, that will lead to different types of stainless steel, which has the best properties related to that. But obviously, corrosion resistance is the starting point. That is the reason why you're selecting a stainless steel. Secondly, you have the service temperature. Not all the different types of stainless steel can be used at very low cryogenic temperature or very high temperature. So the service temperature is important as well. Thirdly, mechanical strength. And obviously, if you want to have, if you want to fabricate a pressure vessel, you can benefit from high strength to be able to reduce the wall thickness. So weight reduction would be possible when you have higher mechanical strength. And then, of course, fabricability, important. If you cannot weld the material, then you very much limit the use of it. And then, of course, surface aspect, we will talk about that as well, that with the stainless steel, you can have very sophisticated surface appearances, special surfaces, and so on. And of course, cost, we're coming to there. We heard that in the introduction as well. Cost, and especially life cycle cost, and when we're talking stainless steel, is an important aspect, especially if you compare to other grade. When the initial cost is higher, you benefit in the long run over the life cycle. But today we will mainly focus on the implication for corrosion resistance, and to some extent service temperature and mechanical strength. And yes, stainless is not always stainless. Stainless can corrode. And whether corrosion will occur or not, and the type of corrosion, depends on a combination of the environment during service cycle and the alloy composition. So what we see to the right there is the most common type of corrosion you can encounter of stainless steel, and that is pitting corrosion. And it mainly happens in contact with saline water solution when you have chlorides in the water, and it's getting worse at higher temperature, and then you can suffer from pitting corrosion. That we'll come back to. Then if you are in a acidic environment, then you can suffer from uniform corrosion. So then you will have corrosion evenly distributed over the surface. So this is more like what you get on like rust, red rust on a carbon steel, a uniform corrosion. Then sometimes when you are exposing the material at high temperature, and that is for the austenitic stainless steel, but also ferritic stainless steel, the lower alloy, you can suffer from intergranular corrosion. That is, corrosion happens between the grains in the microstructure due to chromium depletion in the grain boundaries, and that we will talk more about in the next session, but it will be mentioned here today as well. So what we also mentioned in the beginning in the introduction, we have something called the pitting resistant equivalent, the PRE number. This is a very good way, a theoretical way to rank different stainless steel's resistance to pitting corrosion. And the formula we are using for the PRE, there are a few different ones, but this is the most common one. There you can see which alloying element is beneficial to improve the resistance to pitting. And first of all, obviously, it's chromium. Secondly, with a greater effect is molybdenum. And thirdly, with the greatest effect, it's nitrogen. So if you increase the content of these elements, you will improve the pitting resistance. Now we haven't talked about the different grades yet, but I will explain how we can calculate this number of different grades. But first I want to tell you about that. What I talked about when you're adding at least 10.5% chromium is that you will create this passive film when you have oxygen present. Unfortunately, this passive film is not perfect. There are weak points in the passive layer. It can be due to inclusion and other particles being there that will actually make the film weaker, so it's thinner at some location. If you are then in a chloride-rich environment, those, I would say, evil chloride ion will search up those weak points and can sometimes penetrate through the passive film. If you have a good alloying element, it could be that it will self-heal and repair again. But at some point, when you have a high temperature and a lot of chlorides, it can penetrate through the passive film, and it will create this pit-like defect. And what makes it worse is when the chlorides penetrate through the passive film, the metal ion will go into solution, and this will create an accelerating process where the pH will drop due to the metallic ion and the release of hydrogen ions, which are positive, and will attract more chlorides. The pH will drop, so it's an goes faster, will accelerate, and eventually actually can grow through the whole thickness of your steel plate and create a leakage, for instance. So really, this is something that shouldn't happen, and illustrate why it's so important to select the correct grade, to have the right alloying composition for the environment, and that is really to avoid initiating the pitting. So if we're looking at how do you calculate it, now we haven't looked at the different types and grades of stainless steel yet, but the most common one is the 304 type that I think you have heard about. We will see later on, we call it a core 304. Typically you have 18% chromium and 8% nickel. So that means if we're looking at the PRE formula, nickel will not contribute to the PRE value, but the chromium will. So the 8% chromium gives you a PRE of 18. If we're then looking at the ferritic for 30 type grade, where you have 17% chromium, the PRE will be 17. If we're then finally looking at the duplex grade 2205 type, and as the name implies, it has about 22% chromium. The 5 is 5% nickel, but also 3% molybdenum and 0.2% nitrogen. So if we calculate the PRE, we said we get 22 units from the chromium, plus then we have 3% molybdenum. That will be about 10 units for the molybdenum. So then we are at 32, and then 0.2% times 16 for the nitrogen, and then we add 3 more units, and then we are on the PRE value of 35. So there you see the beneficial effect of the alloying in the duplex grades to increase the PRE number. But we will see later on in the next session we have, where we focus more on corrosion, that this is a good first attempt to rank the grades, but that there are other methods that actually is to be preferred. Then we were talking about mechanical resistance, and there what you need to consider is strength and ductility. And normally to measure strength and ductility, we do a tensile test, and for that we need a steel specimen. Normally it has more like a dog bone shape, the whole specimen, but this is the section where you actually do the measurement. So you have the original length here, L0, then you apply a load to it, and then you will stretch the specimen. So if you unload it again, it will go back as long as you are in the elastic deformation range. It will behave like a spring. So the maximum load you can add there to create a stress in the material where you still have only elastic deformation, that is the limit where we have the RP.2 value, the proof strength, or what is called for carbon steel, the yield strength. So that is the limit where you have only elastic deformation. And typically the value you would use when you design something, you don't want to have permanent deformation into your structure. But if we increase the load even further and we go beyond this point, we will have plastic deformation, and even when we unload, we will have some permanent deformation still in the structure. And of course, that you don't want to have on a bridge, for instance. If you have a heavy truck running over and you get permanent deformation, that is not good. So this is when you add a load, so you get to the maximum before the fracture, you reach the ultimate tensile strength, the RM value. So that is the ultimate strength prior to fracture. And if you look in then how much you actually can elongate the specimen before the fracture, you see the final length is L, and you looking at the difference between L and L0 divided by the original length, then you get the measure of the formability of a material, or actually the fracture elongation, where you're using the A value, and then there are some different ones. If you are familiar with steel, you could be A5, A50, A80, and so on, depending on how long the original length is, the LO0 value there. So the most important metrics here is the RP.2 value, proof strength. RM is the tensile strength, and the A value is the elongation to fracture. So then perhaps it's time for some more questions.
Yes, that's right. So we have the answer from the first question, and 70% of the people, they have given a correct answer, which was 10.5% is the minimum chromium percentage which is required. So now we have second question, which is flashing in our polling, and all of you are encouraged to give an answer. Question is, which alloying element is normally not added to ferritic stainless steel? It's a nickel, molybdenum, or chromium. So Rahul, do we have answers now? because it is valid only for 30 seconds. So everyone has to answer quickly. Yeah, now we have the answer. It's a mixed response because I think question was a bit tricky. 44% people feel it is nickel, 30% feel molybdenum, and 12% feel chromium. So class, what is the right answer, and can you give some
Yeah, it's a
explanation?
bit tricky. We will actually come back to it, but I mentioned when we're talking about the alloy element, which are austenite stabilizer, and the most important one there is nickel. So normally you will not add nickel to a ferritic grade, where you will instead go for the ferrite stabilizers like higher chromium or molybdenum content. So it's nickel is the correct answer.
Okay, so thank you very much. So maybe Rahul, we can have one more question. Yeah, so the next question flashing is pitting resistance equivalent PRE number is not depending on which alloying element. Is it chromium, nickel, or molybdenum? Yeah, time is over now. Let's see the answers. Okay, so 60% of people have mentioned nickel is not making any impact on PRE number. 18% says molybdenum and 8% says chromium. So class, what is the right answer?
Yeah, the majority has the right answer there. It's nickel is not included in the pitting resistance equivalent formula there.
Very good. Okay, so majority of the people are giving right answers. So we will continue this kind of poll after a few slides, and for the time being, we can continue with the presentation.
Okay, thank you, Rajev. Now we have started to talk about the different types of stainless steel. If we're looking from our product portfolio, we are using what we call product ranges to categorize the different types of steel from its properties. So now I will try to link so you can better understand how you can select the best type of stainless steel for a certain type of properties. So if you were in our first session of this training last time, I think Deepak introduced our product portfolio to you. And here we have them divided into what we call the classic products and the pro products. Our classic products are divided into 3 different product ranges. It's the Moda, Core, and Supra. And the differences here, I mean, one of these product ranges can actually include both ferritic grade and austenitic grade. The important thing here is that this should be a help for the material selection, because honestly, for you, it's the properties, the characteristic of a stainless steel that is of importance for you. It's not really the structure, if it's ferrite or austenite or a duplex structure. So therefore, here we want to emphasize that the Moda would be the most cost-efficient choice when you have a mildly corrosive environment, and Core is for an intermediate corrosive environment, and Supra is where you are in a highly corrosive environment and need higher corrosion resistance. So that is typically the classic family includes the more commonly used stainless steel on the market that you can buy from all producers of stainless steel. But then we have our more specialized product, and we have put into the family, the Pro family there. And we started with the Ultra, which continues from Supra, but here it's for the most extremely corrosive environments. And then we have the special grades Therma, where you have high service temperature, when you're above 550 degrees C. Then we have the Forta. That is where you need the highest possible strength, but also in combination with the good corrosion resistance. And then we have the Dura. That is where you need highest hardness, the highest wear resistance. And then we have Product to improve machinability, and Deco when you're in need for special surfaces. So if we start with the ferritic stainless steels, and you can see there up in the right corner that you actually have ferritic grades within all the product ranges within the classic family. So you have ferritic grades in Moda, Core, and Supra. But most of them are actually in the Moda and are suitable for mildly corrosive environment. And how can we link that? So standard ferritic grades, there you typically have a chromium content from 11 to 21%. You have a low nickel, as one of the question was earlier there. And with this chromium content, you can have a PRE number from about 12 to 25. Obviously, if you only have chromium, then you need to have 12, but then you're adding some other alloying element like molybdenum. You can go higher there. So molybdenum is also important to increase the corrosion resistance of the ferritic grades. Then you have some special grades, high temperature ferritic grades. I will not talk more about them, but there you are adding higher carbon content is important for high temperature properties, and silicon, as I mentioned earlier, is important for the oxidation resistance at high temperature, and also aluminum. Typical application for the ferritic grades are in the home appliances. We see that to the right there, a drum of a washing machine, pots and pan, and that is something we have seen more recently, the 10-20 years we go back. Most of this type of application in home appliances were actually designed using austenitic grades, but there's a shift to more cost-efficient use of ferritic grades there. So we see a great use of ferritic grades into those applications. And then in automotive, for the exhaust system, ferritic stainless steel are used, and also for architecture. And of course, due to their limited corrosion resistance, it's mainly for indoor applications. So if we're looking then at the most commonly used grade and the grades we have in our product portfolio, and as you can see there, with increasing corrosion resistance going upwards in this slide. So if we're starting there from the bottom, the most basic stainless steel is what we call the Moda 410L 4003. There you have typically 11.5% chromium. So you are just above, so you make sure you can create the chromium oxide layer on top of the steel there. But of course, a limited corrosion resistance. If you then add more chromium, so you reach about 17% chromium, you will increase the corrosion resistance, as we know from the PRE index. And then we have the most common ferritic stainless steel on the market, and that is what we call the Moda 430. And so according to the ASTM type is 430, UNS number S430 00, and according to the European standard is 1.4016. So what you see in our way of naming the products, Moda, you have the type number first 430, and then you have 4016, which is actually, if you remove one point, there is the European number for that grade. If you then, from a type 430 grade with 70% chromium, adding some titanium, you will have the grade what is called the Moda 439, and there you will have an improved weldability, also improved intergranular corrosion resistance. What you see also, you have the counterpart also for the lower alloy, the 410 grade, where you add titanium, you get the type 409, and with the titanium there as well improves most importantly the weldability, but also the intergranular corrosion resistance. If we then adding more elements, higher chromium content, also niobium, that means when you're adding the titanium, niobium, you will stabilize the structure and you will improve the weldability even further. And by adding more chromium, you will improve the corrosion, and with the niobium also the oxidation resistance at higher temperature as well. So this grade, the type 441, core 441, and there you have significantly better properties than you have from the standard 430. And then you can continue with the grade that we have developed. We call it core 4622, but it also fits to the UNS number S44330. And this grade, you increase chromium further to improve corrosion resistance and the weldability from the stabilization of niobium and titanium. So now note that with the grades 441 and 4622, we have entered into the core range. And the core range means that you have the higher corrosion resistance than you have of the Moda range. Core is typically where you have the 3 or 4 type of grades. Then you can relate it to where we are on the corrosion resistance scale. So we are approaching the corrosion resistance of a 3 or 4 grade here, or actually on pair with 3 or 4 when we're talking about this core 4622. Then the highest resistance of a ferritic grade, at least what we produce, is entering the supra range, and that is supra 444, or what is called in the European standard 1.4521. A lot of numbers here. Here you will have the highest possible corrosion resistance and a good weldability due to the stabilization from titanium niobium. So here is not only chromium adding to the corrosion resistance, also molybdenum. So with a supra 444, you will reach a corrosion resistance similar to that of a type 316 austenitic grade. So you have a good range here actually among the ferritic grades, whereas the big volumes is more on the one that is included in the Moda range there, and the most common one is the type 430 grade. So here you can see a list of all the grades we have in the Moda range. I will not go into detail here. What we can note there is that in the middle of this one, you can see the performance, and there you have something called the grade family. So you see that all of them is indicated with an F, means that they have a ferritic structure. So to summarize, the ferritic grades, characteristic properties, even though you don't have the same formability as you would have for an austenitic grade, the ferritic grade actually have a good deep drawing properties, which means that they have good properties for pots and pans, and that is one very successful for application for ferritic grades into pots and pans, where you can utilize the good deep drawing properties. With the ferritic structure comes a relatively low toughness. The ferritic structure means that you will have a transition from ductile to brittle behavior somewhere just below the sub-zero temperature. So that needs to be considered. The ferritic structure also means that you have a magnetic stainless steel. So that is an important way of actually understanding that it could be a ferritic grades, that it's magnetic, but not always true that the austenitic grade can actually also be magnetic sometimes, but I will come back to that. But ferritic grades are always magnetic. With the ferritic structure comes also a lower thermal expansion than you have on austenitic grades. That can be very useful for high temperature use when you have, let's say, high fluctuation in temperature, so you can actually keep the thermal expansion on a lower level to avoid thermal fatigue, for instance, that can actually crack the material. Also with the ferritic structure, you have a higher thermal conductivity, and once again, that is beneficial when we're talking about pots and pans, where you can benefit from the higher thermal conductivity. And the downside with the ferritic is that you only have, I would say, a limited weldability. Thinner gauges can more readily be welded, but not thicker. And of course, what we said earlier, by adding stabilizing element like titanium, you will improve the weldability. Then we continue with the austenitic stainless steel, and as you see, they are the most commonly the most common structure, and you have actually grades within 4 different product ranges. The core for intermediate corrosive environment, supra, highly corrosive environment, ultra for extremely corrosive environment, and also therma for high service temperature. And we will go through all those 4 different ranges. But typically you have chromium content here in the standard austenitics up to 18%. You have nickel content up to 10%, molybdenum up to 3%. So you can reach a PRE up to 26 for the supra range there. But then you have the more, let's say, special austenitic grades. They are highly alloyed, a higher molybdenum content. They're also typically alloyed with nitrogen. So there you have a PRE span from 28 all the way up to 56. So significantly higher PRE values can be provided there. Then they have the special one for high temperature. There you don't want any molybdenum, but it's preferable to alloy with silicon and rare earth metals like cerium. And the importance starts somewhere at 550 degrees and can be used up to 1150 degrees C. The austenitic grades are used in all different types of application, from food and drink to the process industry, for transportation, to different types of architecture. As we can see there on the cladding on the top of the Chrysler building to the right there, giving a very long service life with a minimum maintenance need. So starting looking at the compositional and property relation for austenitic stainless steel, we're starting with the most common stainless steel on the market, and that is the type 304. So there you have typically 18% chromium, 8% nickel, ASTM type 304, UNS 304 as the standard grade, and according to EN is 1.4301. So if we have this grade as the basis, the starting point, and then we can consider if we want to have higher mechanical resistance, what type of grade do we have then? Or if we want higher corrosion resistance, what do we do then? And what options will we have at that if we do that? Or we can go for higher oxidation resistance by adding some elements to see which type of grades we will get then. But starting from the type 304, we are as the most important grade of the core range. So if we're first looking at what happens if we add some element for the mechanical resistance, starting then from 304, we're adding nitrogen. Nitrogen, we heard earlier, will raise the mechanical strength, and it will also increase the strength at lower temperature. So here we have grades that can great benefit be used for cryogenic tanks where you can utilize strength, but you need good properties at low temperature. And there you have grades like Core 304N and Core 304LN. So you have nitrogen added there. What the L indicates there, I will come back to, but there are similar grades added with nitrogen. Then we can also increase the carbon slightly, sorry, reduce the nickel and chromium slightly, which you will have what is called a more unstable structure. That means that if you do cold working, that you will have plastic deformation of your material, you will actually increase the strength easily. And also actually when you go with cold working and then increasing the strength of this material, you will actually also get the magnetic material. So you will actually transform the austenitic structure partly into martensite, which is magnetic. So that could typically be when you stretch form the material, perhaps to manufacture a zinc. So in the area where you have a lot of cold working, you will increase the strength and it will also become magnetic. But it's not a ferritic grade, it's actually martensite. So you have transformed some part of the structure from austenite to martensite. Then you also can add nitrogen on carbon to a grade we call 301LN. So you actually improve the corrosion resistance slightly. This core 301LN is a very popular grade to be used within the railway industry for rail car bodies, because you have a good combination of strength and corrosion resistance. Both those grades, core 301, core 301LN, by this instability, so by rolling them and having a plastic deformation and reduction of the steel, you can easily get them in what is called temporal condition, which means that you will increase the strength significantly. And by doing that, by definition, you will actually enter our Forta range. So it's still an austenitic grade, but you temporal it, so you will transform the structure partly into martensite, and you get much higher strength, several times higher strength. So you will have what is called the Forta 301 in different temporal conditions. You can tailor the strength, but on the expense of the formability of the material. So of course it's a trade-off there, how much strength you want and how much formability you need. Then finally, if we increase the nickel instead, you will enhance the forming properties, and then you will have the core 305 grade or type 305. So there you will have significantly higher nickel for very advanced forming operations. And then if you add sulfur, you will enhance the machinability, and then we enter what we call the product range, and the product range is suitable when you have a lot of machining. So there sulfur is an important alloying element. So here you can see just by adding a few small amount of alloying element, you can change and improve specific property of the type 304 material. Then if we're looking that we want to improve or increase corrosion resistance from the 304 level, we can add molybdenum, or you're typically adding molybdenum, which has a great effect. And then you will enter the supra range, and the most common grade there is the type 316 or 4401. Another way is with a grade that we have developed ourselves. Here you boost the chromium, you increase the chromium even further, you add nitrogen as well, and also some molybdenum, but not to the same extent as you do for the type 316. And with this grade we call the Supra 316 Plus. It's also included in the ESDM standard and ASME standard as 31655. So here you can benefit from both higher corrosion resistance and mechanical strength in this grade. Then we can also consider to improve corrosion resistance, especially when you expose the material to high temperature, in between 580 and 850 degrees C. That could be during welding or heat treatment. Then the material, the austenitic grade, can suffer from intergranule corrosion, which actually is a chromium depletion in the grain boundaries, which make them prone to grain boundary corrosion or intergranular corrosion. So to address this, we have two different ways of doing that. Either you're adding, like for the ferritic grades, you stabilize them with titanium, and from the 304 then you get the grade what we call the core 321. So that is a type 304 where we have added titanium. Or you can lower the carbon content, and then you see you get the L there. So the type 304L, the L means that you have a low carbon content. And the same can be done also for the type 316, and that you are adding, either you add titanium and you get the Supra 316 titanium, or you reduce the carbon content and you get the Supra 316L. But typically what we are offering, the right hand side there, to lower the carbon content, by the modern way of producing stainless steel in the AOD converter, you can easily reduce the carbon content. So usually those grade like 304, 304L or 316, 316L are dual certified. So they can be used both as a 304L or a standard 304 material. And this has come to that extent that I would say that the stabilization with titanium of austenitic grades becomes obsolete in most cases. So by far the most common is to go for low carbon versions of 304L and 316. as the solution to this problem. So here we continue, and we have the core range where you have PRE from 17 to 22. You see the grades we have here. Once again, you can look at the middle there. You see most of the grade are austenitic, coming from the 304 type. Some has a lower nickel content. We call them the 200 series, where you actually have some nickel replaced by manganese instead. They are not so commonly produced from our side, but they are available as well. And then at the bottom there, you have the ferritic grades there within the core range that I mentioned earlier. Then we have the supra and the most important grades here at the top, 316 and 316L, but you also have this 316 plus there as the first alternative. And what can be seen there in the middle, you have the RP.2 value, and it's significantly higher than you get from other austenitic grade without nitrogen. So it's basically the nitrogen adding to the strength. So you get approximately 100 MPa additional strength by this grade where you have a high nitrogen or relatively high nitrogen content. At the bottom, you also see the ferritic alternative within the supra range as well, the 444. Then we come into the Pro family and the more specialized grade, where we start with the Ultra, that is for extremely corrosive environment. And as you remember, if we add molybdenum to a 304 grade, we get the 316, which increases the corrosion resistance. If we continue on that way, and we adding more chromium, but most importantly, more molybdenum, some nickel is needed as well to be added. Nitrogen, very important here, as improving both strength and corrosion resistance, and sometimes some copper as well to improve the resistance also in acidic environment. But as you see, mainly increasing chromium, molybdenum, and nitrogen actually improves the resistance to localized corrosion. So here we have grades like with 3% moly. You have the 317 type 317 grade, Ultra 317L, or you have 4% molybdenum. You have the Ultra 904L grade, or 6 moly grades. We have the Ultra 254 SMO, and probably the most corrosion resistant grade on the market, the 7 moly grade Ultra 654 SMO, where you have a PRE, if I remember correctly, of 54 or something like that. So very high resistance. Another way, instead of adding chromium, molybdenum, is to add more nickel. And then we actually enter into the nickel alloys, where you actually have more nickel than iron. So you boost the nickel. And actually here we can offer a nickel alloy, the one with 39% nickel, a common alloy called the alloy 825. So that is also in our product portfolio. And we're focusing quite a lot on adding new grades into the nickel-based alloys as well. So here we see again a list of the grades we have within the Ultra range. And as I said, in the middle there you can see the PRE number, and for the 654 SMO there it's 56, so it's very high. Then finally, for the austenitic grades, we have the Therma range for high service temperature. So coming from the standard 304 to improve the oxidation resistance, you have some version of the standard grade where you adding an H there. You have the Therma 304H, you have the Therma 321H. And basically, how do they differ from the standard grades that we have within the core family? With the H, according to the standard, you need to conform to a certain minimum carbon content, which you are not allowed to go below. And very importantly, you need to have a grain size of a certain size to increase the resistance at elevated temperature from 550 up to about 800 degrees C. If you need even higher resistance at higher temperature, you're typically adding more chromium, and you add nickel, and in some grade you're also adding silicon. And the most common grade is the one in the middle there, Therma 310S. Slightly lower alloyed grade is the Therma 309S, and the highest alloy grade here with silicon as well is the Therma 314. But the grade we have developed, which we think in most cases would have the best properties, is the Therma 253MA. And as you can see here, we have also added mechanical strength at high temperature. So with this grade, you will improve both the oxidation resistance and the mechanical strength at high temperature, which actually is the creep strength that will be improved. And that is done by adding silicon, cerium, but also nitrogen, which is beneficial for the creep resistance. But those grades here at the top, they are designed to be used at the highest temperature, typically above 800 degrees C. If you're at the intermediate higher temperature, we also can offer a grade we call the Therma 4910, which actually is a 316 LN type of grade, a 316 with low carbon, with nitrogen. The beneficial effect here is coming from the molybdenum, the nitrogen, but also boron is added here. So if you are at this intermediate high temperature from 550 up to 800, you will have the highest creep strength from this grade, but also good wet corrosion resistance properties. If you are using this material at different temperature ranges, the corrosion resistance in general is also very good here, but also good oxidation resistance and good creep strength at the intermediate temperature range. So this is what we can offer for the Therma range. In the middle there, you have the Ferritic high temperature grade, which was not included in the slide I just showed you, but there are some special grades there that are ferritic, and they are good to be used if you have a sulfur containing environment or sulfur containing gases. They work very good. But otherwise, the most commonly grade here to promote is the one at the top, the 253 MA, that can be used at very high temperatures. So to summarize the austenitic grades, the characteristic properties. So obviously, with a high nickel content, you have the austenitic structure, you have the highest elongation values and a very good formability, as we can see that to the right, to be able to form the bowl of a sink. And as I said earlier, where you have a lot of deformation there in the zinc, the material will transform into martensite, so it will actually be magnetic there, where you have a lot of deformation, whereas in the other parts, typical austenitic grades are not magnetic as delivered, but if you cold deform it, it will become magnetic locally. With the austenitic structure, you also have a high toughness, and that can be utilized also at low temperature. You can use it for cryogenic transportation or storage. You have a high thermal expansion, so that can be a drawback if you are fluctuating the temperature from very high to ambient temperature. You will have a lot of expansion in the material. And also if you want to combine it with the carbon steel for some reason, that can be an issue if you don't consider it in the design, because they will have a very different thermal expansions. You will have a lower thermal conductivity here compared to the ferritic grades. The lower thermal conductivity, that is something that can be utilized, for instance, in a thermos. For a thermos, of course, you want to retain the heat or retain the cold liquid. And then, of course, it's good with low thermal conductivity. They are easy to weld a machine, and they can be used for a wide service temperature range from cryogenic to very high temperature service. Okay, so that was the austenitic grades and the product families connected to those. Then we have the duplex stainless steels with alloying composition, where you have a high chromium content, relatively low nickel. You have addition of molybdenum and nitrogen to increase the corrosion resistance, but also the strength related to the nitrogen. So you can get PRE values from 16 up to 43 here, a wide range there. So with the two-phase structure of a duplex grade and the nitrogen addition, you can reach high strength. So the Forta range is where you have RP.2 values from 400 and above. And as I said, also the temporal austenitic is actually part of the Forta range. Applications typically like bridges, pressure vessel, large storage tanks, industrial piping. So where you have high pressures, you will get high stresses, you need high strength. But also into reinforcement bar, it can be utilized. So the most common grade within the duplex type of grades in the Forta range is the 2205 I mentioned earlier. 22% chromium, 5% nickel, 3% molybdenum. And in the American standard ASTM and ASME, you have two different numbers. It's the 31803, and then you have one S32205. And the S32205 more restricted into a higher alloying composition with like a higher nitrogen and better corrosion and mechanical strength than the counterpart to the left there. So the first attempt with the duplex to make a more linear composition was that one at the bottom there, the Forta duplex 2304. There you have slightly lower nitrogen content and lower molybdenum content, and of course that will affect that you have slightly lower strength and lower corrosion resistance. So by increasing nitrogen, increasing molybdenum to the 2205, you will improve the properties. If you go even further, adding more nitrogen, you're adding more chromium, molybdenum, in some cases also adding other elements, you will reach the super duplex grade, where we have the Forta Super Duplex 2507, but also the Forta SDX 100. So these three are the most common duplex stainless steel on the market. Then we have optimized a version of 2304. We call it EDX Enhanced Duplex 2304, where you have within the chemical range of 2304, we have tried to optimize the composition with the highest possible nitrogen chromium content to get best possible properties for both mechanical and corrosion resistance. Perhaps most important thing here more recently is the development of lean duplex grade. And there we were the pioneers, and we have the Forta LDX 2101, lean duplex 2101. In this type of grade, you remove the nickels. You only have about 1.5% nickel, and instead of the nickel to keep the phase balance, you are adding manganese and you're adding nitrogen. You're increasing the strength by lean alloying, but you're not reducing the corrosion resistance to a great extent compared to 2304. So you get a very cost-efficient alloying there. Then you can also play around with this lean alloying composition to also get a duplex grade with better formability, and that we have with our Forta FTX 27. Or you can go, instead of trying to get a more leaner alloying composition than the most common duplex grade 2205, and there we have the Forta lean duplex 2404. Also here we are reducing expensive alloy element like nickel and molybdenum. Instead, we are increasing chromium, nitrogen, and manganese to get highest possible strength, but also a corrosion resistance very close to 2205. So here as well, we have the portfolio of duplex grade. Note that the temporal material is not included here, but they are also part of the Forta family. But typically what you can see in the middle, the RP.2 value is more than double that you have of the standard austenitic grades. So summarizing the characteristic properties of duplex grade: high strength, that means a high RP.2 value, high tensile strength. You still have a good formability, not as good as the austenitic grade, but still very good, especially for this FTX 27. You have a high toughness, but it's a mixed structure of ferrite and austenite, so it drops at sub-zero temperature, but still can be used typically down to -40 degrees C. It's magnetic from the ferritic structure. You have a lower thermal expansion than the austenitic, so they can be more easily combined to carbon steel, low thermal conductivity, and a good weldability. So if we're all looking at comparing the different ranges, looking at the performance strength on the vertical axis versus corrosion resistance on the horizontal axis, you can see that if you want to have the combination of higher strength and corrosion resistance, you go for the duplex grades indicated by the green dots. If you want the highest possible corrosion resistance, you go for the ultra range indicated by the orange dots there. If you want to have the best possible elongation properties and formability, here you see, of course, you should go for austenitic grades like the 304, 316 grades indicated with blue there. Or if you need corrosion resistance as well, you go for the ultra range indicated by the orange dots. And you see that ferritic grades and duplex grades are lower on the scale there on the elongation.
Class?
Yes?
I think we have reached to the time limit. So
okay, sorry.
It will be very good if we can, because I think most important topics are covered for today, and we can take a look at some of the questions which people have asked, and then we can try to answer them.
Yeah, go ahead, Claes. You wanted to say something? Yeah.
No, sorry. No.
Okay. If we have to take question and answer, let's begin with some of the questions which has been asked in the beginning itself. Let me go through it. Okay, so we have a question from Mr. James. Is the self-healing, it is just, I think it was in the beginning itself, is the self-healing of stainless steel effective if carbon steel rusts particles on SS? I hope you understood the question. Is the self-healing of stainless steel effective if carbon steel rust particles are on SS?
No, that there you need to be careful. If you have carbon steel contamination of a stainless steel surface, of course, that is negative, and that can actually affect the corrosion resistance that you locally actually can have pitting corrosion where you have those contamination there. So it's very important to have a good hygiene, to not use the same tools as you are using for carbon steel when you're working with stainless steel. So to try to keep the surface clean. So the most important is to have clean surfaces, and then to have oxidized oxygen in the atmosphere to repassivate the oxide layer.
Okay, thank you. Then another question is from Mr. Sumant. He has asked two questions. One is, what is the salt water test criterion for stainless steel, number of hours, and what is the limitation of molybdenum content in stainless steel? So I think the first part of the question, which is asking about salt water test criterion for stainless steel and number of hours, let me tell Mr. Sumant that you have asked the question, right question, but if you see that the next series is on corrosion resistance, and we'll talk about more about on this topic right from the beginning. So what is the limitation of molybdenum content in stainless steel that you can take?
I don't know exactly the limitation. The highest alloying limit we have for molybdenum is for our Ultra 654 SMO, where we have 7% molybdenum. And with that grade, you reach a corrosion resistance that's approaching that of nickel-based alloys. So the highest we have is 7% molybdenum. I don't know how much you can go beyond that, actually.
Okay, so thank you. Then the next question is from Mr. Sabrish Nair, and he's asking, can you please elaborate if there is any negative effect of molybdenum?
Yeah, molybdenum could be very much negative if you are in an environment that is more alkaline and hot nitric acids, for instance, very oxidizing environment that you also can encounter within, for instance, pulp and paper industry. There actually the molybdenum will have a negative effect. So for high pH and alkaline environment, and like hot nitric acid, then you should select a grade with a low molybdenum content or without a molybdenum content. So then it's better to go for a lean duplex grade, for instance, or
Yes.
standard 3 or 4 in some cases.
I think it was answered very well. And next question is from Mr. Suresh, who asks, which grade of stainless steel sheets and plates are recommended for architectural application which needs mirror finish, brush finish with a very good weldability properties?
Yeah, if the surface quality is of highest importance, the best grade is to use the standard austenitic grade, where you also have very good weldability. So depending on the corrosion resistance you need there, if an outdoor environment, it depends on how close to sea and so on. Of course, the 316 is most commonly used for outdoor environment, but also 3 or 4 can be used if it's less corrosive. But 304, 316, and the austenitic grades are the best one to use if we're looking at the surface quality as well as weldability.
Yeah. So the next question I can see is from Mr. K.R. Anant Narayananji. He's asking, when Ferritic has a good deep draw property, is roping in drawn part an issue, especially for cookware?
Yeah, that is a very important question. I said that deep drawing properties are good for ferritic grades, but roping is still an issue. But they're actually our latest development, what I mentioned as the Core 4622, where you have very high chromium content stabilized with niobium and titanium. There you actually will will have less roping than the traditional ferritic grades, according to our insight so far. So it could be a solution to go to this special grade.
Since it is a very interesting topic, just quickly, can I add a question on my own? What is that the grade which you mentioned with higher niobium content? How much it reduces the roping if compared to other grades in same?
Sorry, say it again. What was the?
What exactly reduces that roping when we talked about some of the grades which you have developed?
Yeah.
Do you have any idea?
The content of niobium, you said, or?
Yeah, so what it does?
Yeah, we can. Yeah, the roping index, you said, or?
Yes.
I don't have it here, but maybe we can come back to that later on.
Sure. So the next question is, what is the maximum temperature where stainless steel can be used? And related question, of which grades?
Yeah, the highest temperature depends on the environment. So if we are in pure air, so a very clean environment, then the Therma 253 MA or 314 can, in best cases, be used up to 1150 degrees C. But of course, then if you have other elements in the environments there with water, steam, and things like that, or other elements, then of course that can be reduced. But in best cases, in pure air, it's 1150.
Right. Another question, we can take 2-3 more questions. So another question is from Venkat Chalam. He is asking requirement of NACE, NACE applicable on SS. It's a question. What requirement additionally added for compiling NACE? Could you read the question?
I'm not sure.
I think he's asking about some of the requirements stipulated in NACE, NACE, but I don't know which requirement he's talking about. Anyway, you can, Mr. Venkat Chalam, if you can put your question further, I can ask in the end. So the next question is, which is the most corrosion resistant material for architectural application, like cladding and all, stainless steel or aluminium? Actually, the question is choice between stainless steel and aluminium for hand railings for architectural applications.
I'm not sure if I'm the right one to answer it, because I would of course say that stainless steel has clear advantages there, especially on the corrosion resistance side there, and also providing a more durable surface. But then of course it comes to also if you can benefit from a lightweight structure using aluminum as well there. So but in most cases I would prefer the stainless steel therefore.
There are some questions in chat box also, so let me ask one or two. This Mr. Siva Prakash is asking why we have to select RP 0.2. I mean the 0.2% proof strength.
Compared to yield strength or
yes. Compared to yield strength, yes.
Yeah, the reason is that typically the austenitic stainless steel, they don't have a defined yield point like you have more for carbon steel. So it will be a transition from elastic to plastic behavior. So that will be not be a sharp point there. So then you need to define a yield strength, and that you're doing by looking at where you have 0.2% permanent deformation. So when you can allow 0.2% plastic deformation, that is how you define where you have your proof strength or yield strength there. So that is needed due to the characteristics of austenitic grades, but also the duplex grades.
Yeah. So there are 2-3 more questions, but let me tell the audience that from Rashmi, and there is another question from another gentleman. So they are asking chloride content in seawater is also a criteria for selection of the right grade of stainless steel. If yes, what is the selection data and criteria? And another question is regarding, it's a very typical question, that we have brown coloration coming in on 316L grade for certain reasons. And how can we avoid Tundi's nozzle closing in grade 3 UNS 30815? So all these questions we are going to cover in our next of the series, especially the corrosion series. So I'll request you, those who are asking these questions, please join our next series, which will be next month, and you will have greater understanding and good knowledge on those corrosion aspects and selection criteria. So other last question, if we can take, this has just come from Mr. Chetan, which is best replacement for ASS dot FSS or MSS? So I think it could have been he could have elaborated a little more on the question so that. So I think, would you be able to answer based on this? So
I'm not.
Austenitic, which is the best replacement of austenitic stainless steel? Ferritic stainless steel or martensitic stainless steel? I think this is what he wanted to ask. ASS, FSS, and MSS.
Yeah, sorry, it's difficult for me to follow and actually understand the question there.
Just let me clarify very quickly because we are running short of time. I think, see, if you have to replace a grade between different class families of the stainless steel, like from austenitic to ferritic and austenitic to martensitic, you must have understood that there are many grades available with different mechanical properties and corrosion behavior in other than many other technical aspects. So once we go into corrosion resistance part and understand the corrosion better with respect to grades, we'll have greater insight into which grade can replace which grade in some of the or equivalent grades in other selection criteria. So it's a advanced question, and I request you to join the next session also on corrosion part so that this becomes more relevant. So I think we have covered all the questions and all the I think even from the chat box also. So with this, we would like to come to the part where we would end this session. Before that, let me once again thanks Claes for being there very early morning and giving this wonderful talk on the grades. And we will also like to thank Outokumpu team, Rajiv ji and Deepak Vaidya, who was also there. Apart from that, many thanks to all the participants who has taken time from their busy schedule to be a part of this learning and educational series. Thank you very much. We look forward for the next series, and we will announce the dates very soon. Thank you very much. Thank you all the panelists also.
Thank you.
Bye bye.
Yeah.
Thank you.